Okay. So clearly, if you're talking about Mars, you got to talk about rocks. My background is actually in biology, and we don't know that there's any biology on Mars, or if there's ever been any biology on Mars, but we clearly know that there is geology on Mars. And so I want to talk just a little bit about the different types of rocks, and a little bit about characteristics. For the lab this afternoon, we will focus exclusively on igneous rocks because that's her favorite. Clearly, igneous rocks are an important component of the landscape on Mars. I'll point out some examples of sedimentary rocks as well. We're probably just as interested, if not more interested, in sedimentary rocks on Mars if we are interested in life in the past, because clearly igneous rocks don't maintain fossils, whereas sedimentary rocks do. But let's just go through some of this. Don't want to spend a lot of time talking about principles of rock formation because it's not a physical geology class. But generally speaking, a couple of key points here. Rocks are made of minerals, very broadly speaking. And so, especially when we're talking about igneous rocks, the way that those igneous rocks crystallize from molten magma or lava is going to influence the kind of minerals that are present in those rocks, are going to determine the characteristics of the rocks. Now, besides rocks being essentially made of minerals, rocks over time can undergo various transformations as minerals get moved around or transformed. So these minerals that are part of the rocks can undergo transformation over time. Various minerals can be depleted or added to rocks depending on their history. So we can think about movement of these minerals. And the other main thing I just want to get across on this slide is that geological processes in general occur over geological timescales, but basically for most of the landscapes we see, for most of the landforms we look at, those are going to be the process of slow, gradual processes that have worked for long periods of time. Now we know that there are every now and then catastrophic events. So there is some balance between catastrophism and uniformitarianism, but generally speaking, we understand the history of geological processes by looking at the geological processes we can see going on today. Things like eruptions and crystallization of magma into rocks, and the slow weathering of rocks, and the accumulation of sediments to produce sedimentary rock, and so forth. So it's if you have the right time scale, it's more interesting than watching paint dry, but it's clearly kind of on the same order of processes. Okay. What are the main classes of rocks for those of you who had earth sciences before? Igneous, sedimentary. It's right up here, okay? So basically, we can take pretty much any rock type and categorize it based on the processes that gave rise to that rock. Okay? So when we go out and we look at rocks, we're basically building up a story of how that rock came to be in the location that it came to be in. Why would we bother classifying rocks?
So we can understand how geological formations are.
Okay, that's part of it. Why is it important to know whether a rock is igneous or sedimentary or metamorphic? Bertram, what were you going to say?
Those are big.
Go ahead. Yeah. So, I mean, scientists do a lot more than classify rocks. If you're a biologist, you classify organisms.
By classifying different types of rocks, you're able to determine their origin from their beginning or research. Like igneous rocks are from lava, which come through the mantle, so it gives you like a little sense of what the mantle may consist of.
Right.
Looking at the rock
Okay.
on the surface.
So yeah, one very good point there is these igneous rocks we see on the surface are basically samples from an environment that we cannot go down and actually make direct measurements on. Generally speaking, nature is confusing and messy and very diverse. So one important aspect of trying to just make sense of the world around us is to say, well, what kind of groups can we classify these different items into, whether they're animals or species or rocks or seashells or whatever. Classification is oftentimes a very important first step in trying to just make sense of this bewildering array of different rocks or different species or different organ types or other kinds of areas that different scientists would like to study and to make sense of. So yes, clearly with rocks, we're talking about three basic rock types. We've got igneous rocks, which I've characterized here with this image of a solidifying lava flow. The key characteristic of igneous rocks is that these are rocks that crystallize directly out of molten rocks, and we'll talk more about that process. Sedimentary rocks are rocks that build up from materials that have come from other rocks. So we have a process of weathering, either chemical or physical, that breaks down rocks, produces sediments, and those sediments over time can in turn turn into new sedimentary rock types. Characteristic feature of most sedimentary rocks is that you can probably see the layers of sediments that were laid down over time. And then there's this other category of rocks that is not going to be as important for our discussions of Mars, metamorphic rocks, which are other kinds of rocks that have been transformed through the action of high pressures, high temperatures, but not high enough temperatures to actually melt the rock into magma. Because if that happened and that rock then, that magma then crystallized, what kind of a rock would we have? Igneous. Okay, so pretty straightforward. As I said, we'll focus mostly on igneous rocks when we go down to the lab. So again, these are rocks where we've got, let me switch over to a red pen. We've got some molten magma underneath the surface of the planet. And if the density of that magma is lower than the surrounding rock, it's going to tend to try to find its way upward through cracks in the crust. And we've got really what I want to focus on is three different categories of igneous rocks. So we could have the situation where the molten magma breaches the surface, at which point it is no longer called magma. What's this molten material called when it actually comes out on the surface? Lava, okay. So volcanic rocks are rocks that solidify at the surface from cooling lava. Okay. Because this is happening at the surface, that lava tends to cool relatively quickly. And because it is cooling very quickly, the rock really doesn't have time to create very extensive and large crystals. Jalen?
Is there any actual difference between magma and lava other than where they are, or is it the naming system?
To some extent, it's naming. To some extent, if the molten material is underground, we still call it magma, and we call it lava when it is up on the surface. But you have to realize that during the ascent of the magma, it alters, it changes. So if you look at the composition of magma deep in a magma chamber underneath the ground, it's going to have a different composition than the lava flows that are at the surface. As the magma rises, pressures are generally going to decrease, and so gases that might have been forced into solution in the magma down deep under pressure, when that reaches the surface and pressures decrease, oftentimes those gases come out of solution, form gas bubbles, and outgas from the magma as it is going higher and higher in the magma chamber in the chimney of the volcano, for example. You also have the magma oftentimes changing temperature, beginning to cool. So those minerals that have the highest melting temperature are the minerals that are going to crystallize out first. And so the remaining magma is going to be depleted in those high melting point minerals. So the composition is going to change. Also, as the magma comes up through the crust, imagine you've got all this hot lava going through this crack in the Earth's crust. It's quite likely to be pulling stuff off of the sides of this crack. And so you've got other materials being added. So generally speaking, composition does change as the magma rises through the crust. And so to some extent it's semantics, below ground magma, above ground lava, but there are clear compositional differences as well. Okay. So, the first type of igneous rock, volcanic, cooling at the surface, exposed to the air, rapid cooling, small crystals. That's as opposed to, and this should be a 2 here, plutonic rocks. So there are situations where you've got magma that will accumulate under the surface and not actually find its way to the surface and become a lava flow, but still cool off, have the rocks solidify. Cooling is going to be faster or slower for these blobs of magma that are retained underground? Slower. Okay, so these rocks are going to crystallize more slowly, which means that you have more time for larger crystals to form. And so plutonic rocks tend to have a more obvious crystalline structure to them, whereas lavas that solidify at the surface tend to cool very quickly and they don't have that obvious crystalline structure. And I want to add one other category here that we're going to call pyroclastic. If you've got magma coming up and it's under reduced pressure and these gases are coming out, you can get very explosive eruptions of material where the solidifying globs of lava are thrown out into the atmosphere. And these pyroclastic rocks that form as a result of that, it could be ash, it could be tephra, it could be bombs, depending on the size of the rocks and materials that are being formed. But oftentimes, because you've got this molten stuff thrown out in the air with continued outgassing, you get the incorporation of air bubbles in the rocks as they're forming. Okay, so as I said, we find a lot of volcanic rocks, especially volcanic rocks on the surface of Mars. Mars has had billions and billions of years of volcanic eruption. And so here, this figure is the landing site for the Pathfinder rover. Which was the reading assignment either for today or for last session. So I wanted to, really focus on the. If you look at this plane, it's a lot of mostly volcanic rocks just scattered all over the place with some sand and dust mixed in. Those volcanic rocks would have been the result of extensive lava flows that came out on the surface of Mars. And then impact processes over time oftentimes will break up that surface layer of volcanic rock, forming various sized pieces of fairly angular bits of volcanic rock, basalt, andesite. Other kinds of volcanic rocks. This is Gusev crater, where the Spirit rover was sent. From orbit, Gusev crater looked like it was a lake-filled crater, which they sent the rover there with the hope that it would land on all of these lake sediments. But apparently, sometime after the lake dried up, billions of years ago, the whole area was just covered by lava flows. And so when they got there, it was very disappointing because there wasn't much to look at the initial landing site beyond just these volcanic rocks. And so instead, they sent Spirit off to these hills on the horizon, without thinking that it would necessarily ever get there. Of course it did. And so Spirit made most of its more interesting observations, discoveries over here in the Columbia Hills, which are named after the Columbia astronauts who were lost in the shuttle accident. Okay, so that was volcanic rock, again, very important for Mars, which is why we're going to focus on igneous rocks in the lab today. But as I mentioned, we, to some extent, might be more interested in sedimentary rocks for their potential to incorporate fossils. So the big thing with sedimentary rock is, of course, that you've got other rocks being broken down either by chemical breakdown or just physical processes, so freezing and thawing, water getting into cracks in rock and freezing and expanding and breaking the rocks open. Those will lead to a variety of sediments and dissolved chemicals. And then those sediments and chemical solutions can undergo this process of lithification to form new sedimentary rocks. So if you've got sand grains being deposited on the bottom of an inland sea, over time those sand grains will build up into layer after layer after layer of sediments, and as the pressure builds up on those layers, the pressure or the compaction can, and as well as chemical processes, can cement those grains together into basically new layers of rock that were formed from these sediments. Okay, so we are beginning to look at some sites on Mars that deal with sedimentary rocks. Here is the Opportunity landing site. Opportunity rolled to a stop on its bouncing airbags in this crater called Eagle Crater. And the rover was activated, it stood up, it started taking pictures, and the first thing it saw in Eagle Crater was this layer of bedrock. And bedrock is critical for geologists because you know that those rocks formed in place at that location. You know, all of the rocks that are in the Pathfinder site, all the rocks that were present at the initial landing site for Spirit were rocks that were produced elsewhere probably and deposited there through various processes, impacts, or flash floods in the past. But here was a case where, you know, one of the first cases where we actually saw bedrock showing through.
This is random and has nothing to do with rocks, but in terms of Mars's sky, what color is it? Because in that picture it's white.
Yeah, it is. This is not too bad representation of the color. And Ben, we're going to go past 5, so don't jump at 5. Yeah, go. No, don't bother, because I already see we're not going to make it. Yeah, this image has been color balanced a little bit. What you would see with your eyes if you're standing on Mars would be probably something in between. But in the bedrock, we saw layered sedimentary rock here. Here's a later crater that Opportunity went to, Victoria Crater, and looking at the walls of the crater as it's eroding here, you see these different layers of sediment that are laid down. Similarly for Curiosity rover, it is heading toward Mount Sharp. That's not the official name, but that's what the mission specialists call it. And the reason why Gale Crater with Mount Sharp in the middle was selected for the Curiosity mission was the presence of, you know, several kilometers worth of sediments that had built up to then be eroded away to form this Mount Sharp structure. So, based on the principle of superposition, which of these layers of sediment is older, down here at the bottom or up here at the top? Bottom. Okay, so once Curiosity gets to the base of Mount Sharp, it's going to spend a lot of time looking at these old layers because these represent very early Mars. And so these sedimentary rock layers can hopefully tell or allow the mission scientists to reconstruct what conditions were like, you know, 4.5 billion years ago when those rock layers were laid down. And then because there are, you know, all of these kilometers of rock layers, the plan is to have Curiosity climb the mountain looking at younger and younger layers of sediments to see how conditions, to actually document very closely how conditions changed over the history of Mars. So that's one thing that these sedimentary rock types and rock structures are useful for. Just like in the Grand Canyon, we're planning to do the same thing here with Mount Sharp. So because we're late, I'm not going to say much about metamorphic rock. I'm also not going to say much about metamorphic rock because a lot of the production of metamorphic rock is involved with various plate tectonic movements that bury rocks deep enough to heat them up and put them under pressure without melting them. And what have we talked about plate tectonics on Mars? Not much, if any at all. So, I mean, there are conditions that will lead to some metamorphism of rocks on Mars, but it's not going to be as extensive as what we see around here. Actually, I live up in Connecticut. If we're talking about eastern New York and Connecticut, pretty much all of the major rock outcrops around here are metamorphic rocks. They are various kinds of sedimentary and igneous rock that have been modified over time by being partially buried to heat them up and put them under pressure. So just quickly, we have this basic rock cycle where the different kinds of rocks can be transformed into one another. As we've talked about, if we start here with magma underground or lava above ground, as that magma or lava cools, the type of rock we form will be igneous rock. That igneous rock can be converted to metamorphic rock if it gets exposed to high pressures and temperatures warm enough to change the rock without melting it. On the other hand, if it gets hot enough, it's just going to go back to magma and then be recycled back into new igneous rock. Weathering of igneous rock or metamorphic rock or other sedimentary rock produces sediment that can be lithified by compaction and chemical alteration to cement the materials together to form sedimentary rock. And of course, sedimentary rock can be converted into various kinds of metamorphic rocks by heat and pressure, as can metamorphic rocks also be converted to other kinds of metamorphic rocks if they're exposed to the right conditions of temperature and pressure. So we have this basic rock cycle. It really all stems from, I like to think of it as starting with molten rock. That's going to lead to igneous rock, and then various processes can transform those igneous rocks into metamorphic or sedimentary rocks, and eventually it's all going to get recycled back into the crust, down into the mantle, melted back to molten material to form igneous rock again. Okay, so this is the last slide, so we won't go over too far. But in terms of focusing specifically on igneous rock, we can classify igneous rock on the basis of a couple of properties. We already talked about intrusive versus extrusive, that is volcanic rock, which cools at the surface, versus plutonic rock that cools underneath. But there's also this other gradient here between felsic and mafic rocks. Okay. So igneous rocks can vary quite a bit in the amount of silicate material that they've got in them. Okay, so silicates, these are lighter minerals. And so depending upon the constituents of the magma, depending upon the experiences, the conditions that magma experiences as it moves up through the crust and does or doesn't break through the crust to the surface, the resulting rocks are going to have either a higher or a lower proportion of this lighter silicate material. Okay, so the felsic rocks have more silicate. That's an arrow up. And they're going to therefore be composed of minerals that are lighter, less dense than is the case for the mafic rocks. So less silica and more heavy elements in their minerals, iron and magnesium, calcium, and so forth. So, the mafic rocks tend to be darker, and the felsic rocks tend to be lighter colored, maybe even pinkish, and they're going to be, the felsic rocks are going to be less lower density rock, and the mafic rocks are going to be higher density rock. So here I've got a couple of examples of igneous rocks. Here we've got, well, I'm not going to tell you what it is, but just looking at it, would you expect that to be more likely to be a mafic igneous rock or a felsic igneous rock? Mafic, because it's dark. You can't pick it up, so you can't tell how heavy it is, but on the other hand, we've got this igneous rock, which is clearly a more felsic rock. It's going to be composed more of these lighter minerals, and therefore is going to have different properties because it's formed under different conditions. So go ahead, yell now, Ben.
Wait,
506?
506, it's not that fun now.